All right, let's continue the review here. 4.5 deals with stoichiometry. So in stoichiometry, the main thing we're doing with is trying to figure out if you can calculate how much product is going to be formed either in grams or in moles, or likewise, you should be able to calculate how much of a reactant you're going to need from a given amount of, say, a product that you were obtaining. And so let's take a look at this example that we've got here. We've got an example here that asks us to go ahead and use this balance reaction. And we need to find out how many grams of the carbon monoxide, which is one of the products that's going to be produced if you start off with a mass of 68.3. Now, in this particular problem, we're provided the mass of one of the reactants. And so what you need to be able to do here is to anticipate also the type of problem that might give you the mass of both of these reactants, because at that point that would be a limiting reactant type problem, and you would need to figure out which one runs out first. So let's use this as the baseline, and then we'll modify this problem and then pretend that we have starting amounts for both and try to figure out the limiting reactant from there. So in this particular problem here, we have a starting amount of 68.3 grams that's provided here of the very first compound. And so that means that this particular compound here, we have a mass of 68.3 grams of this compound, C2H3F. Now, the main thing that we want to do first is any mass that's provided to us, we want to make sure we convert that into moles. So the very first step here is we're going to go ahead and take this out and convert this into moles. And we'll say that for every 1 mole of this compound, C2H3F, it's going to have a certain mass of C2H3F. And in this particular case, if we add up the mass here, figure out the molar mass for this. And so let's kind of do a generic here, C2H3F. The F is going to have a mass of, I believe this is going to be roughly 19 if I round it to the nearest whole number. There's 3 hydrogens, so 3 times 1 is 3. And then the carbons here, 12 apiece, 12.01, but rounded up to 12. Times 2 is going to be 24. So if I add all these numbers up here, I'm going to get up a number here. Let's see here. What's the 24 is 27, plus 10 is 37. 37 is 3 is 40. And that should be about 46 grams overall. Go ahead and add that up on your calculator and see if that's the case here. 46 grams per mole of this particular compound. And let me just double check that on my end. Okay, so that value is correct. So we're going to take this value here, this 46, and we're just going to add it right there at the top. So let's go ahead and do that now. We'll put that there as 46 grams. And then what will happen here is the gram unit cancels out. And so the number that we get here is going to be the number of moles of this particular compound. Now, we could just go ahead and do that and do the math. And so I'm going to go ahead and erase some stuff we don't need here at the bottom. And so if we do that math there, we're going to take 68.3, divide that by the 46 down here at the bottom. And that should give us a value of 1.484 moles of C2H3F. And this is how much we have at the start. Okay, so it's important that we do that. Now, if we consider the equation here, or the ratio in the reaction, we have the following. So let me change the colors here so we can see it. So we have 4 moles of this first compound, and that is related to the compound in question. We're after carbon monoxide. So the ratio here is a ratio of 4 of the starting compound to 4 moles of the carbon monoxide. So the way I set up the problem here, we first calculated how many moles we had. You could have easily done this and continued on in the stoichiometry setup. And so what I'll do here is I'll just do this as a second step, and then we'll do the ratio down here at the bottom. And so in this particular case here, for the second part here, we know that we've got 4 moles of the C2H3F is related to 8 moles of the carbon monoxide. And so we go ahead and cancel the moles of C2H3F, and so that will lead us with the answer of moles of carbon monoxide. Since the problem is asking for grams, the last step here that we want to set up is try to figure out what's the molar mass of 1 mole of carbon monoxide. So what we do know is that oxygen has a mass of 16, carbon is a mass of 12, and so that tells us here that 1 mole of carbon monoxide has a mass of 28 grams of carbon monoxide. And so when we do that, here we're going to get the moles of carbon dioxide canceling out, and that should allow us, let me move this, make this a little bit smaller, make some room here. And so when we do the math here, we're going to multiply 1.484, and we're going to multiply that by 8 divided by 4 times the mass of 28. And so that'll give us a mass here of 83.104 grams of CO produced. And so that would be the answer for us there. And so this would be the stoichiometry process that you want to utilize when you're trying to figure out problems on how much of a product is produced. Now, we could go backwards and we can use this mass then and try to figure out, but let's go ahead and take a look at this same problem, but kind of set it up in the sense that what if we started off with equal amounts of C2H3F and the other compound at the beginning, oxygen. So we try to figure out which is the limiting reactant. And so in this case, what I'm going to do is I'm going to go ahead and modify this problem for us so that we can actually do that math. And so let's go ahead and erase this. All of this information, let's go ahead and delete all of this. And we'll start off with a brand new slate here. And I will go ahead and adjust our mass here. Let's say that instead of 68 here at the beginning, we're going to change this just so we can have the same amount. Let's go ahead and cross that out. And instead of 70, we're going to say maybe 50 grams of that compound, but we're also going to say that we're going to start with 50 grams of oxygen. And so now what we're faced with is we're faced with a limiting reactant type problem because we've got the mass of not only the first compound, but we now have the mass of the second compound. Notice the starting mass here in this second version of the problem, we've got grams to start. So the very first step is to convert everything to moles. So let's go ahead and do that for both of these compounds. At 50 grams of the C2H3F, we'll do that one more time here. So we'll say 50 grams of C2H3F. And this is going to be for every 1 mole of C2H3F. That's going to have a certain mass of C2H3F. And if you recall the mass that we just did here in the previous problem, we said that the fluorine was 19, the hydrogens were 3, and the carbons collectively were approximately 24 grams. When we add all those up, we had a mass of 46 grams. Now, this is going to be the number of moles of the C2H3 that we have at the beginning. So we take the 50 divided by the 46, and this will be just above a gram at 1.086 moles of C2H3F. So that's actually above 1 mole. I think I just said grams, but it should be moles. We'll do the same thing for the other compound here, the oxygen. So we'll start with 50 grams of the O2 and do the same math here. For every 1 mole of oxygen gas, we're going to have a mass here of 32 grams of the O2. And so when we do the math here, what winds up canceling is the grams of O2. And our value here is going to be just a little bit more than 1 mole. So we'll take 50 divided by the 32, and that will give us 1.562 moles of O2. And it's important that we label these here at the start. Okay. And in order for us to figure out which one of these is going to run off first, what we will need to do is to pick one of these two compounds at the beginning. Either we're going to go with C2H3F to begin with, or we're going to choose the oxygen to go first with. I would say since the first reaction component here is the C2H3F, let's start with that. So if we start off with this amount of C2H3F, how much of the oxygen do we need? And so in order to do that, what we'll need to do here is we'll need to adjust. And so let me make some space. Let me minimize that for a little bit. And we'll say here that if we start with the 1 mole or 1.86 moles of C2H3F at the start, we're asking ourselves, how much of the oxygen do we need? And so we already know the mole ratio here. Notice the mole ratio is 4 of the C2H3F to 7 moles of the O2. So we'll say here, for every 4 moles of C2H3F is going to require 7 moles of O2. And so that will allow us to cancel the moles of the C2HF or H3F, and then that will allow us to calculate the value. And so that value, then when we go through it, we're going to take 1.086, we're going to divide or multiply that by 7, and then we're going to divide by 4, and that should give us a value here of 2.075 moles of O2 needed. And so that's an important number for us, because now we're in a position where we can compare how much of the oxygen we need. Let's change the color here. We need 2.075 moles of oxygen, but we have at the beginning 1.562. So here we can see that the oxygen is going to be running out. And so the way we do that mathematically, just to make sure that we have the math set up, is the following. Let's make some space here. Let's minimize this just a little bit. And then we'll do here at the very bottom, we'll do the math here. And we'll say, based on what we need, well, actually, we'll start off with a half value. We have 1.562 moles to begin with, and we need 2.075. If we subtract the half amount from the need, notice here that the value that we're going to get is a negative number. And so because it's the negative number, that means that the oxygen is limiting, because these values here represent oxygen's values. And so that means here we can actually come back over here. We can say that this value here is the limiting reactant. Okay, so if the problem is asking you which is the limiting reactant, this is where you're going to stop. Now, in this particular problem, we had originally asked how much of the carbon monoxide would be produced. Now that we have 2 masses for the beginning reactants, we just determined which one's going to run out first. So as soon as the oxygen is run out, that means that the products that are going to be formed are also going to stop being produced. So we can now make a determination that if 1.562 moles of oxygen is the limiting, based on this number, we can now calculate how much carbon monoxide is going to be produced. And so therefore, we can do the following work. Let's do the work at the bottom. Therefore, based on that number, 1.562 moles of O2, we can now figure out how much carbon monoxide is going to be produced. The ratio between the limiting reactant and the carbon monoxide is this. So it's 7 moles of oxygen to 8 moles of carbon monoxide. So that means here 7 moles of oxygen for every mole. 8 moles of carbon monoxide is going to be produced. And we need to take this all the way to grams. And so we know that 1 mole of carbon monoxide is going to have a very specific mass. That mass we had said 16 for the oxygen, 12 for the carbon, is going to give us a mass of 28 grams of carbon monoxide. And we'll break that up and we'll cancel everything that can be canceled. Moles of O2, moles of carbon monoxide. So the units that we're going to have at the very end are grams of carbon monoxide. So what we'll do here is we're going to take the 1.56, we're going to multiply it times 8, divided by 7, times the 28. And when we do that, that number that we wind up getting here at the very end is going to be the following. It's going to be 29.785 grams of CO produced. And this is going to be based on the limiting reactant of this problem. So those are the steps and sequences that you're going to use in order to identify limiting reactant products formed, or rather, that's the way you find out how much product is formed based on the limiting reactant. The last piece that you'll need to do here is perhaps maybe go the opposite way. So if you already know how much product is produced, is try to figure out reverse order how much reactant you're going to need. Now, I'm not going to show the math here on an example, but you would set it up just the same. It's a reverse type stoichiometry problem. As long as you know the starting material, use the mole ratios to go backwards from the product side over to the reactant. I do want to make sure I take a moment here to explain how to do the percent yield, as that is also a type of problem that you could encounter here on this particular quiz, exam, or section. And so let's do one of those fairly quickly here and identify that. So what I'll do here is I'm going to go ahead and erase the items, and then I'll come back here and with a brand new problem on the screen. So here is a percent yield problem. Let's take a look at this here. What we've got is we've got a balanced reaction here at the bottom, and they're telling us that we have 99.7 grams of nitrous oxide here, so one of the reactants on the left-hand side. It produces 174 grams of NO2, nitrogen dioxide, over here on the product side, and they're asking us what is the percent yield. So for these types of problems, remember the percent yield formula is the percent yield is equal to the actual over the expected. We're going to multiply that by 100, and that should give us the percent. So it's important that we identify what is the actual amount and what is the expected. So in this particular problem here, since the reaction of 99.7 grams of NO is provided, notice here it says produces, so this amount here, the 174, is actually what is produced in this reaction. So this value here, this here is our A value. That's what was actually produced here in this reaction. So that means that the value of 99.7, this is what we're going to use to find the value of E, or the expected. And then we're going to use those values in the formula here and here to calculate the answer. So let's go ahead and figure this out. The value is in grams for the actual, so that means we're going to use this 99.7 and figure out the stoichiometry to get us to the grams of product that is going to be produced, or how much we expect to get there. And so here we'll do the math. We'll start off with the 99.7. So that's 99.7 grams of NO. And then we're going to use this and convert it first to moles. So that means that for every 1 mole of nitrous oxide, that's going to have a certain mass of nitrous oxide. And so what we'll do here is take the mass of the oxygen, which is 16, and we're going to add 14 for the nitrogen. That'll give us a mass of 30 grams. And so we're going to put everything in one line. And so let me extend this line one more time. And so the next step is, now that we know the moles of nitrogen and oxygen here, or nitrous oxide, we need to know the ratio between this compound, which is one of the reactants, and the product we're interested in. The ratio here is a value of 1 to 3. So in the next section, we'll say for every 1 mole of nitrous oxide, we're going to say that we're going to produce 3 moles of nitrogen dioxide. Since we're after the mass, the next step in the conversion is to take the molar mass of 1 mole of nitrogen dioxide, so that would be 1 mole of NO2 is going to have a certain mass of NO2 in grams. And so that would be 16, 2 of them, that will give us 32 for the oxygens, and then we'll add 14 for the nitrogen for a total mass of 46. And that should give us the mass that we expect to get. Cancel what can be canceled. So the grams of nitrous oxide, same here, and O in moles cancels out, and then the moles of nitrogen dioxide cancel. So the final unit that we have, or the answer, should be the grams of nitrogen dioxide. So what you want to go ahead and do is go do the math all the way across. You can multiply all the numbers in the numerator first and divide by the product of the denominator. And so let's kind of work on the answer here. So I'm going to take 99.7 multiplied by 1 divided by 30, and then I'm going to multiply that by 3 divided by 1, multiply that by 46. And so that should give me an overall final answer here. And I'll put this in purple, and that should give us a mass of 458.62 grams expected of NO2. And so this value here is the value that we want expected, or that's how much we should get. Now, by looking at this, if you're only getting 174, we expected 458, that's going to be a very low value. But let's go ahead and calculate the percentage here. So we'll take the percent yield is equal to the actual, and that value was 174. Remember, this is in grams. And then we're going to take 458.62 grams, and this is going to be multiplied by 100%, or 100, and that'll give us the answer there. We can go ahead and cancel out the unit of grams, and so that'll give us a value If we take the 174, we divide it by 458 and 62, that value there should be, this section here should be 0.37939. We're going to multiply that times 100. And so the final answer, when we actually do all of that, that final answer here, I'm going to put this also in purple. That answer here should be at 37.939. Let's simplify this. The answer here should be, if we're going to go just to maybe 3 sig figs or a whole number, depends on how the question is answered here. Since they give us 3 sig figs at the beginning, let's go ahead and report 3 sigs. So it'll be 37.9% is what we're looking for here. And then the compound here is going to be NO2. And so here is our answer for this particular problem. So in all, you've seen how we've been able to use stoichiometry, which is nothing more than a conversion process involving chemical reactions to either predict how much product we're going to get, to determine how much reactant we need, or you're using it within a limiting reactant type setup where you're trying to figure out which reactant runs out first to determine the products formed. And then lastly, here in the example we just did, try to use the stoichiometry so that we can actually get a % yield in terms of product that we are expecting to get relative to how much we actually got. So as long as you're using the formulas here, using the stoichiometry correctly, remember that the units should cancel. The only unit that you should have at the very end should be the units that you're after. So when you set up your stoichiometry here, all of the units need to cancel, and the only unit should remain here should be the one we're after. So in this particular example here at the very end, we wanted grams of nitrogen dioxide, and that's what we had used, what we determined in the overall setup. So with that, though, that brings up 4.5 to an end in terms of our review. Continue with us here as we continue the review on 4.6 in the next video. Yield.